Hello, my name is Sergei Zuyev. First of all, I would like to thank the organizers for making this conference happen in this uneasy situation. I do hope that one day and sooner or later I will visit in person incredible place, Karelia, and enjoy your company in person. The model that I'm going to present you today has origins in colloidal chemistry. In chemistry, colloids is a mixture of molecules which are dispersed in a volume without settling down or coming up to the surface. There are two processes which the molecules in this volume may undergo. First of all, the two molecules may join together by creating a bond between their atoms, or better to say, between the terminal atoms, which allow for linkage. On the other hand, there is also a disaggregation of the molecules. This happens when a bond in the molecule breaks, and so the molecule disaggregates into two pieces. Mathematically, we describe the process by the system that consists of n elements, which we call atoms. The atom may form a molecule of size n, and we call these n atoms, and we assume in this model that the atoms consisting of n atoms only formed by linear arrangements of atoms. So it is a linear sequence of atoms with n-1 bonds between them. The endpoints are the terminal points which allow for a connection to other molecules. So the molecules may join only by the end and create a longer molecule. Mathematically speaking, the evolution, the time evolution, is described by a continuous time Markov chain, x of t, in the state space of vectors of the following form. It is a vector of size n, capital N, as the number of atoms, where nk is the number of k molecules. So the number of molecules consisting of k, exactly of k atoms. Of course, there is a restriction that the total number of atoms in the system is still n, so it means that the sum over k and k must be n. When the molecules combine by creating a bond between the terminal atoms, this happens at certain rate. So we think that every molecule searches to bind to another molecule at the rate lambda, which is a parameter of the model. So an N molecule fuses to an R molecule at rate lambda to create N plus R molecule. You may also think that each pair of molecules fuse together at the rate 2 lambda, independently of their sizes and all the other molecules. The destruction of the molecule is described by the bond breakage. So the bonds break with rate 1. Of course, 1 is immaterial. You can always just reparameterize the time so that the rate equals 1. And ultimately, lambda will also change. So it's not a big deal to consider that it is 1. An N molecule consists of N atoms. So it does have, in a linear arrangement, N-1 bonds. So it means that an N molecule disaggregates at rate N-1. An important property of a Markov chain is the so-called reversibility. So I just recall you that a reducible Markov chain with states 1, 2, 3, etc., and transition rates q, I, j is called reversible if the following identity holds in distribution. So for all time instances t0, t1, and tn, if we consider the reverse time, so we consider the time t0 minus t1, t0, etc., minus tn, so this means that x t0 minus t is a distributional of copy of x of t. And so hence is the name reversibility. It's quite an important property. Of course, not all Markov chains possess that, but as soon as they possess, we can actually write, at least theoretically, the probability, the stationary distribution of this Markov chain. First of all, the Markov chain is reversible if and only if there is a probability distribution pi of I such that the so-called balanced, detailed balance equations are hold. So basically you see that this is the rate at which the flow from the state I to the state J. So it is the transition intensities weighted with respect to the frequency of being at the site I. So flow from I to J equals to the flow backwards from J to I, whatever pair of states I and J are considered. In this case, this pi of J is actually the stationary distribution of the Markov chain. The Kolmogorov criterion gives a machinery to check if the Markov chain is reversible or not. It states that for any cyclic sequence of states, so we going cycle from I to I1, from I1 to I2, from IN to I back to I. So this is a cycle, and the product of intensities of going along the cycle in one direction, so from I to I1, from I1 to I2, etc., should be equal to the product of intensities of going backwards from I to IN, from IN to INS minus 1, and again until we reach I. This criterion implies that the stationary distribution of this Markov chain could be expressed by the following formula. We fix some state I naught, and then the stationary probability of any state J equals stationary probability at these selected sites I naught multiplied by the following ratio. In the numerator, we have the product of intensities of going from I0 to IJ to J, and in the denominator, we have the product of intensities going backwards. And of course, this formula depends, similarly depends on the way we are getting from, on the path we're getting from I0 to J. But the balance equation actually means that whatever path you select, the Pj will be the same. What does matter? It does matter in the choice of the path is that to choose such a path where these expressions could be easily written. And that's the key point of the proof of the theorem that I'm going to present below. So the main idea how we prove and establish the reversibility of this chain, we well, first of all, we select a particular node I naught, which is here, yeah, and then we define cleverly define the path along which we can produce this compute this intensity, the product of these intensities. Then now, so we can just express some quantities pi j using this formula. The question is whether this is a stationary distribution or not of the reversible Markov chain. It will be if such found quantities pi j satisfy the detailed balance equation. So actually, as soon as we have computed this pi j using formula 3, then, and using our choice of path, then we check if the detailed balance equation holds, and if it does, we are lucky. So we have found the stationary distribution, and we have proved that the Markov chain is reversible. Okay, so now let me pass to the result. In the Markov chain that describes the molecule system of n atoms, the Markov chain is reversible. Its stationary distribution satisfies this formula in red. And what is this? You can recognize here this particular states we have chosen. The particular state just consists of n atoms and of course no molecules. Here in this formula you see that of course lambda is there, so the rate at which the molecules fuse. Here it is raised to the power the total number of links in the state n. Of course, it depends on how many molecules you have. So if there are nk molecules of size k, consisting of k atoms, so they have k minus 1 bonds. So this is the total number of links or bonds in the state n. The idea of the proof, as I said, so we just take this state as a starting state. And then how do we get from this state to any state n1, etc., consisting of n1 atoms and 2 molecules of size 2, etc., and n molecules of size n. Of course, it could be only one. The way we get there is we create the molecules. So first of all, we create the longest molecules by joining atoms together until all the longest molecules are created. Then we pass to the next smallest size molecules until create them all, etc. So let me exemplify this by the picture. So this is a system consisting of 9 atoms. So we start with 9 atoms only, so there's no molecules. And the, say, state that we want to get to, for instance, this state. So there's 1 atom, 1 molecule of size 2, and 2 molecules of size 3. So you see that there are 3 molecules of size 3, 1 molecule of size 2, and 1 atom molecule of size 1. From N0, so we first, you see the longest molecules has size 3, so we want to create first molecules of size 3. So we start creating the first one, so we join this atom together, we get that state. Then from that state, we add another atom to the this molecule of size 2, so we constructed the first molecule of size 3. So now we start constructing the next molecule of size 3. So these guys join together, then this guy added. So we have created all the molecules of size 3. Now the next size is size 2. So these 2 guys join together to create a molecule of size 2, and we are done. And it appears that it's quite easy to write down the transition intensities here. Most importantly, to get back along the same route. So this guy first must break, and that guy break, this guy breaks, etc. So actually, by doing this, we have found the presented distribution by this formula. We can do more. We can do more here. We can actually, one of the most probably important features here is how many molecules is there. Let's call this M. This is a random variable, of course, and under stationary regime, in the stationarity, it has the following distribution. So the probability, the stationary probability that the number of molecules is M conforms to this formula. So you see that the first term here is just the normalizing coefficient. Then the lambda, the rate of joining, is in the power minus m divided by m factorial, and here comes the binomial coefficient. So, well, when you sum these things so that it gets to 1, so the normalizing coefficient can actually be expressed in terms of the so-called generalized Laguerre polynomial of degree n minus 1 here and alpha here. So another parameter here is 1. So it's a standard, more or less, function. The distribution is unimodal, actually, with a model point which could be expressed explicitly. It is done in the paper, but basically, as n goes to infinity, it behaves like square root of n over lambda. So that's the order of the things here. So the Laplace transform is also could be written explicitly. So it is given in this formula there. And the first 2 moments are also computed. So again, they are expressed in terms of the generalized Laguerre polynomials already with alpha equals the corresponding k. So you see for the first moment, it's Laguerre with alpha 2 divided by Laguerre with 1, etc. This is how the things look like. So these are theoretical results. Here, the system consists of 100 atoms. And on the right, the 10,000 atoms and different lambdas. So, well, here, for instance, you see that 100 and lambda is 001. So theoretically, we say that we know that the mode has order square root of n divided by lambda. So it is n divided by 001. So square root of 10,000, so it's 100. So it has orders of 100, and you see, yeah, well, it's not really 100, it's a bit smaller, but this is just an order of the things. And of course, lambda is smaller, in this case, n over lambda, bigger, n over lambda is smaller. So you see that actually the distribution shifts to the left. On the bottom here, you see the simulation studies. You see that actually the simulation result conforms very well to the theoretical ones. Also, of course, the number of atoms is important characteristic, but it doesn't say all the story. All the story says the distribution, the stationary distribution that I showed you in the first theorem. But we may be interested in the configuration of molecules when their number is fixed. And for this, the length of the molecule, given their total number is m, actually conforms to the symmetric multinomial distribution, but which is conditioned on the set that the total number of atoms is n. So otherwise, you see it's explicit expression here, not very cumbersome. So what happens when the number of atoms becomes very large, so when it grows? In this case, actually, we can show the convergence to the normal distribution if we normalize and center the distribution of the number of molecules properly. So properly means actually that the corresponding shift and also the variance should be of order square root of n over lambda, still the same order that we have seen. Moreover, by the standard methods, you can also find the local central limit theorem. It says that if the number of molecules, so if m has order square root of n, then when n goes to infinity, it could well be approximated by the density of the normal distribution with the parameters an and an over 2, as in the previous, of course, result. So as you see next, and the order is O small of root of the power 4 from the number of atoms. So here is the last plot that I'm going to present you. So you see here the scaled probability mass function. So these are blue dots, which are superposed with the corresponding approximating normal curve, normal distribution. So you see that the agreement is very good. And the more the number of atoms, so on the left here we have 10,000 atoms, on the right side we have 1 million atoms. So you see that the bigger n, the better is agreement, of course. In the end, I must first of all say thank to my master students who actually did the simulation, the results that you saw, and actually they also inspired me to return to this problem. This model was presented to me by a chemist some time ago, and it was a kind of in a dormant state. And when I decided, okay, why not to give this for the students to play with? So they started to program, we started to discuss, and this way kind of come back to the problem and discover the results that I have shown you. I was very much disappointed to actually discover that the stationary distribution in the first theorem was actually found already by Frank Kelly back in 1979. And even in a more general situation, actually, he considered not only linear arrangements of atoms, so his molecules may be also trees. On the other hand, he does not give any details how he obtained the stationary distribution. He just checks the balance equation. So it is still a mystery to me how he arrived to this formula. Neither he gives any results concerning the total number of molecules, nor the asymptotic behavior of the distribution when n is big. But it's very interesting if his results could be generalized in this direction. Can anything be said about the asymptotic behavior, for instance? Another direction that could be looked at is actually to allow molecules to leave the system. So it's an open system where the number of atoms is no longer fixed. For instance, this may be that small molecules diffuse away and some diffuse in. I bet that the Poisson distribution might appear as at least in the limiting distribution when the system becomes very large. A related result could also be found in the Kelly's book. So I stop here. So thank you very much for your attention. If there are any questions, I would happily answer them.